So this work is a collaborative work with University of Minnesota and Harbin Institute of Technology in China. So let me begin with the background. So IoT, as everyone know, IoT supports diverse applications, including security surveillance, as well as intelligent transportation systems. In order to support those various diverse applications, we have deployed heterogeneous wireless technologies, including Wi-Fi, Bluetooth, and ZigBee, where the body of the wireless devices has been growing rapidly through the last decade, where the Gartner predicts 20 billion IoT devices by year 2020. However, one of the significant side effects of growing wireless technologies is the cross-technology interference, or CTI in short. We have seen CTI degrading various IoT applications, including smart home devices, as well as baby monitors. Where this paper particularly focuses on Wi-Fi CTI. This is because Wi-Fi is the major source of CTI these days, because the majority of the traffic in shared spectrum is Wi-Fi. So the low power IoT, for example, ZigBee, in the range of Wi-Fi CTI is often corrupted. This is due to the significant power asymmetry, which could be as large as 1,000 times. This is an example of Wi-Fi CTI corrupting ZigBee packets with the high power Wi-Fi packets. By closely observing through Wi-Fi CTI, we find two issues that limits ZigBee performance. The first issue is the scattered idle times. What ZigBee needs is a few long idle times. This is because of the scarce traffic of ZigBee and long packet duration. However, CTI says otherwise. Our measurement from a moderate traffic of 700 packets per second, Wi-Fi packets per second, says that under Wi-Fi CTI, what ZigBee actually gets is many and short scattered idle times. This is because we have 700 Wi-Fi packets, therefore we have 700 idle times in between every packet, and 92% of the idle times turns out to be less than 2 milliseconds, which is not useful for ZigBee transmissions. This fundamentally limits ZigBee throughput. Now, the second issue is unreliable CSMA. ZigBee CSMA transmits when idle time is longer than 256 microseconds, which is called CCA. However, CTI often yields idle time between 256 microseconds and 2 milliseconds, which indicates the idle time is long enough to initiate ZigBee packets, but not to complete it. Under this kind of idle time, ZigBee packet is corrupted, where in this particular case, up to 75% of the transmitted ZigBee packets are corrupted. This fundamentally limits ZigBee energy efficiency. However, the issue of CTI has been there for a long time. So why do we have to care in 2018? This is because we now have a new opportunity called cross-technology communication, which is CTC in short. So CTC is a recently announced set of technologies that enables heterogeneous devices to directly communicate. In this paper, we are particularly interested in Wi-Fi to ZigBee CTC, which was announced last year, where we carefully select Wi-Fi payload byte patterns to emulate ZigBee packets. In other words, Wi-Fi packet encapsulates ZigBee packet within its payload. This works on commercial devices without any hardware firmware changes on both transmitter or Wi-Fi and the receiver, which is ZigBee. So now let's move on to ECC design. To start with, let me give you a brief overview. So ECC resolves issue 1 of scattered idle times using clear to send, or CTS, defined by Wi-Fi standard. Using CTS, ECC generates long idle times that can be utilized by ZigBee by aggregating many scattered idle times. Next, ECC resolves the second issue of unreliable CSMA by explicitly notifying channel availability to ZigBee via CTC. This essentially enables TDMA between Wi-Fi and ZigBee. Let me give you some details starting from the idle channel aggregation via CTS. CTS enforces nearby Wi-Fi to back off and buffer packets. So using this, can we actually aggregate scattered idle times to generate long idle times usable by ZigBee? To validate, we test on a physical test bed, and it turns out that after CTS, we can generate long idle time D, and which turns out to actually aggregate scattered idle times and generate dense buffer Wi-Fi traffic following D. This validates that CTS actually indeed aggregates scattered idle times. So the challenge here becomes, how do we set D, which is the duration of the idle time, to non-disruptively to Wi-Fi under inherent dynamic Wi-Fi traffic? In other words, how do we adjust while maintaining Wi-Fi throughput? We note that D causes high contention by buffered packets right after following idle time D. And we know, it is well known, that Wi-Fi throughput is to drop under excessive contention. So to avoid such Wi-Fi sacrifice, we dynamically adjust D depending on lambda and lambda prime, which is the arrival rates measured before and after CTS. This is because the lambda actually indicates the number of processed packets, which roughly indicates the throughput that we want to maintain. The design principle behind this is that when lambda is bigger than lambda prime, that means the arrival rate has decreased after CTS, meaning that it's presumably excessive contention. Therefore, we decrease D. In the other case where lambda prime is bigger than lambda, then there is a possible room left for more contention. Therefore, we increase D. When lambda is equal to lambda prime, that means the D is currently tolerable under current Wi-Fi traffic. Therefore, we maintain D. We iteratively update D via feedback through this equation, where we adjust D. This equation essentially adjusts D towards lambda equals lambda prime, where the update parameter actually indicates the time needed to compensate lambda drop or increase following CTS. After this, the updated D is sent to ZigBee through CTC, where D actually indicates the CTI-free time allocated to ZigBee. This essentially enables TDMA between Wi-Fi and ZigBee. Note that this prevents packet corruption due to CSMA unreliability, which was the issue 2. Another thing to note here is that long idle time of D spans 20 megahertz, corresponding to the Wi-Fi bandwidth, which overlaps with multiple ZigBees. In other words, ECC provides opportunity for multiple ZigBee channels concurrently. To utilize this, we send notifications across multiple ZigBee channels by utilizing the leveraging CTC feature of concurrent transmission. So the CTC works as follows. ECC works as follows. We transmit CTS and ECTC, which basically aggregates scattered idle times to generate long idle time D. And then CTS immediately notifies ZigBees to safely transmit ZigBee packets within that time frame. Let me show you a running demo of our design. It's a very short demo where we first demonstrate, where we first compare ECC with non-ECC, meaning the legacy ZigBee, under the same Wi-Fi traffic of 350 packets per second, and under the same Wi-Fi, the same ZigBee number of ZigBee packets, where without ECC, we can clearly see packet corruptions due to CTI, where with ECC, we reliably transmit ZigBee. And then following that, we show dynamic adjustment of D under different Wi-Fi traffic. On the top, we have higher amount of Wi-Fi traffic of 1,000 packets per second. On the bottom, we have 350 packets per second. We can clearly show that the D is shorter in the top case, where it is currently 18 milliseconds, whereas it is 30 milliseconds under smaller Wi-Fi traffic. ECC on top of this, ECC also provides additional parameters to be fine-tuned for a better coordination, including when and how often to transmit CTS, as well as user-defined Wi-Fi tolerance and application-aware operation. Please refer to the paper for details. So, what is the uniqueness of ECC? Compared to the state-of-the-art commonly use implicit coordination, meaning that it statistically models the history of the Wi-Fi traffic and try to estimate or infer the idle traffic in the future. As opposed to, however, in ECC, we do explicit coordination, where we deterministically define idle channel in time and frequency. What that indicates is that ECC actually removes uncertainty in idle time, indicating higher ZigBee reliability. On top of this, there are potential designs that can be built on top of ECC, including QoS. For example, we prioritize some data to be transmitted within the time frame of D for higher reliability, where we transmit less important data outside D. Similarly, we can improve throughput. We can also enable multi-channel ZigBee. Now, let me move on to the evaluation. This work has been evaluated on 2 commercial devices of laptop and Telos B, which is a commercial ZigBee node, where we evaluate on 2 different scenarios: apartment with moderate Wi-Fi traffic, and university lab with a high number of Wi-Fi users. Let us first see the reliability of ZigBee under ECC, as well as standard, which indicates the legacy ZigBee, and WISE, which is one of the state-of-the-art using implicit coordination. Under regular intensive Wi-Fi, meaning periodic intensive Wi-Fi, the standard falls pretty short, start to fall pretty short. However, seems like WISE, which is a state-of-the-art, seems like it's still holding. However, when there's a dynamic intensive Wi-Fi, the performance of Wi-Fi, which is actually the practical Wi-Fi traffic, the performance of WISE start to drop significantly, which is 60% less than ECC. The reason is because under dynamic Wi-Fi traffic, it becomes much harder to statistically infer the idle time. However, one of the things we need to note is that unlike the theoretical expectation, we only achieve 85% reliability even in ECC. We found that there are 2 practical reasons to this. One is a hidden terminal. And second, there was actually a few Wi-Fi devices that disregards CTS for security purpose. This is because by flooding CTS, we can potentially disable networks. Now let me move on to the coordination performance, where ECC successfully achieves coordinated balance. We can actually see that when we increase Wi-Fi rate, therefore we adjust D to be smaller, which enforces ZigBee throughput to decrease. Also, we see that ECC impact to Wi-Fi remains below 5% under high Wi-Fi traffic, which is 150 packets, 1,500 packets per second. Okay, to summarize, ECC is the first explicit channel coordination, naturally adaptive to dynamic traffic, which is free from any statistical model, and is nearly non-disruptive to existing Wi-Fi, and is compliant to standard and fully compatible with the current commercial devices. And we believe that ECC is a generic technique that can be potentially applicable to different channel coordination between different heterogeneities, including LTE and BLE. That's the end of my talk. Thank you so much.